Hello guys, hope all of you are well in this difficult situation. Welcome to my lecture series. Let me introduce myself first. I'm Rinki Bhaumik, Assistant Professor, Department of Physics, JIS College of Engineering. Today's lecture is for first year. For first year, the paper name is Physics 1 and the paper code is EH101. The name of the paper is Physics 1 and 3 credits. There will be 3 lectures per week. Total 36 number of lectures will be there for all of you. This is for BTech first year, as I said. Now, let me show you your syllabus. This is your syllabus. First, this is module 1. In module 1, there is waves and oscillation. In module 2, there is classical optics, where we have to discuss about interference of light and diffraction of light. In module 3, there is quantum mechanics 1, where we'll discuss about quantum theory and quantum mechanics. In module 4, there is solid state physics 1, where we'll discuss about crystal structure and semiconductors. And in the last module, that is module 5, we'll discuss about modern optics, where there is laser and fiber optics. So this is your syllabus, and these are some books which is recommended for all of you.
Hi, I'm Jennifer Waters, the director of the Nikon Imaging Center at Harvard Medical School, and today is a quick presentation on a very important property of lenses, numerical aperture. Numerical aperture is critical because it limits both resolution and the brightness of your image. In light microscopy, we define resolution as the distance by which two objects must be separated in order to distinguish them as separate from one another in the image of the objects generated by the microscope. And in epifluorescence microscopy, according to the Rayleigh criterion, that distance is equal to a constant, 0.61, times the wavelength of light that is generating the image, so the emission wavelength of light in fluorescence, divided by this property of the lens called numerical aperture, which we abbreviate as NA. Numerical aperture is marked on every objective lens. So right after the magnification, you'll see a slash and then a number, and that number is the numerical aperture of the lens. A numerical aperture is equal to n sine theta, where theta is equal to the maximum angle of acceptance. What that means is, if you think about the light coming from your sample, theta is the maximum angle of light that the objective lens can collect. N is the refractive index of the media that's between the lens and the specimen. So I think we can all agree that a lens is not going to be able to collect the 90-degree angle of light coming from your specimen. So the sine of 90 degrees is 1, and the refractive index of air in a vacuum is 1, slightly higher than that in the room. But many objective lenses have a numerical aperture above 1. So how is that achieved? Yes, Tally.
Raise the refractive index somehow?
That's exactly right, Tally. We use an immersion media that has a higher refractive index, like immersion oil. The refractive index of immersion oil and cover slip glass are similar, both about 1.5. Let's think about how refractive index could limit the numerical aperture of an objective lens. So again, numerical aperture is the maximum angle of light coming from your sample that the lens can collect. So light traveling at an angle through the cover slip, when it hits the interface between that cover slip and the media that resides between the lens and the cover slip, if the refractive index is different, you're going to get refraction. So that refraction can limit the angle of light that the lens can collect. Because immersion oil has a similar refractive index to the cover slip, refraction is minimized. So this allows you to collect those higher angles of light coming from your sample. So this is great. But, very important point here, a dry objective is designed expecting that refraction to occur. So if you oil a dry objective, image quality will actually get worse. So only use immersion oil with an oil immersion objective. Since the maximum angle of light that's collected by the lens increases with numerical aperture, that means that higher NA lenses are going to collect more light from your sample. That means brighter images, which we all love. If you compare two lenses that have the same magnification and the same correction for aberration, but differ in their numerical aperture, you'll find that the higher numerical aperture lens is much brighter. So think about the effect that will have on your experiment. If you choose the lens that has the lower numerical aperture, you'll have to compensate for that decrease in brightness in some way. So you might use a longer exposure time in your camera, or you might increase the intensity of illumination. That's going to cause more photo bleaching and more phototoxicity in a live experiment. Now that you understand how important numerical aperture is, you'll understand why it's important to report it in the methods section of your publications. So lenses should be described as the magnification, the correction for aberration, and the numerical aperture. For example, 60x Plan Apo 1.4 NA. Correction for aberration is the topic of a future video. I hope this has been helpful and that you'll always pay attention to the numerical aperture of your objective lens.
In the last class, we discussed about the optical fiber. There we had discussed about pore cladding, numerical aperture and acceptance angle. Even we had done all the derivation and the formula also we know. Now today we are going to do some numericals. So for all of you note down the numericals. The light enters from air into optical fiber core having acceptance angle 20 degree. What will be the numerical aperture? What will be the numerical aperture of the fiber? In air. So this is the question. Now the acceptance angle is given. So how to do this numerical? First of all, theta A equal to 20 degree and the refractive index, that means eta is also given, that is that the value will be obviously 1. Now eta equal to 1, then the formula is Na equal to n0 sin theta into A. This is the formula of the numerical aperture. So n0 sin theta A. Now n0 the value is 1, sine of theta A equal to 20 degree. So finally the answer, if you put the value in your calculator, then you can get the answer as 0.342. So therefore the answer of the numerical aperture is 0.342. This is the answer. So it's very easy. If we know the formula, we can do the numerical easily. Even all the numericals in optical fiber, most of the numericals are like this. Okay, there is you just have to put the values, then you can get the answer. Now the next problem, let's do it. First you note down the numerical, otherwise you will not be able to understand what you have to do. If any optical fiber has the refractive index of the core 1.4 and refractive index of cladding 1.3, then calculate the numerical aperture in N for numerical aperture, N for numerical, A for aperture of the fiber. So the formula, as we know, before that let's go through the numerical. If any optical fiber has the refractive index of the core 1.4 and refractive index of cladding 1.3, then calculate the numerical aperture of the fiber. Now Na equal to, the formula is Na equal to root over of N1 square minus N2 square. Very simple. Now you just have to put the values. Here N1 equal to 1.4 and N2 equal to 1.3. Now you put the values over here, that is 1.4 whole square minus 1.3 whole square. If you do the calculation, then you can get the answer as root over of 1.19619, 1.9, it will be 6 minus 1.69, 13 square 1.69. So if you do the calculation, then the answer should be 7, 0.27. So finally you find the answer and you please tell, that is your homework. Okay, so this is about the second numerical, and here also you have seen that here you just have to put the values and then you can get the answer. Next numerical, that is your third numerical, all of you note down. A step index fiber has a core index of refraction that is N1 is equal to 1.425. The cutoff angle for light entering the fiber from air is bound to be 30 degree, bound to be 8, it would be 8.50 degree. What is the numerical aperture of the fiber? What is the numerical aperture of the fiber? The next question, what is the index of the cladding of this fiber? Third question, if the fiber were submerged in water, what would be the new numerical aperture? And cutoff angle? So this is the question. First go through it. Well, a step index fiber has a core of refraction N1. The cutoff angle for light entering the fiber from the air is bound to be 8.50 degree. What is the numerical aperture of the fiber? What is the index of the cladding of the fiber? If the fiber were submerged in water, what would be the new numerical aperture and cutoff angle? So the what you first have to do, that is note down that n0 equal to 1.0003. That means you can consider also as 1, there is no problem. Therefore, the numerical aperture Na equal to n0 sin theta 0 max is equal to 1.0003 sine of 8.50 degree. That will be equal to 0.14 into 8. So 0.148 is the numerical aperture. Now the next one is n1 square minus n2 square equal to n a square. This is the numerical aperture. Okay, formula. We already derived in the last class. n1 square minus n2 square equal to n a square. Therefore, n2 square equal to n1 square minus n a square, which will be equal to 1.425, that is whole square, minus 0.1479 square. So if we do it, then finally we can get as 2.0088. So this is about the n2. Now the next one is the numerical aperture. We already have calculated, that is Na equal to 0.148. Now sin theta 0 max is equal to Na by n0. So therefore theta 0 max is equal to sin inverse of Na by n0. So it is equal to sin inverse of 0.1479 divided by 1.33. So it is equal to finally sin inverse of 0.1112. So if you put it in calculator, then the answer would be 6.38 degree. So this is the answer. So as you can see, there is nothing to think. You just have to put the values in the formula, then you can get the corresponding answer. Nothing else. It's very simple. So now let's go to the next numerical. The next numerical is, all of you must note down, a step index fiber has a refractive index one 1.55 and a cladding of refractive index (1.53). Determine its numerical aperture. Now again in the formula you just have to apply the formula, then you can get the answer. Numerical aperture equal to n0 sin theta a, it is equal to root over of n1 square minus n2 square, it is equal to root over of 1.55 square minus 1.53 square. Okay, so that will be equal to 0.24 into 8. This is the answer of the numerical aperture. Very easy, you just have to put the value of n1 and n2, then you can get the answer. Now the next one is, this is fifth numerical. A step index fibre has a core of refractive index 1.50 and a cladding of refractive index 1.40. If the fibre is used in a water, then find the numerical aperture and acceptance angle. So therefore again we have to just put the formula on the calculator, then we can get the answer easily. So the first, Na equal to n naught sin theta a, that will be equal to root over of n1 square minus n2 square. So n1 minus n2 square, if you do it, then you have to put the values. Root over of 1.50 square minus 1.40 square, which is equal to, if you put the values in the calculator, then you can get the answer as 0.53 into 8. Now theta A equal to sine inverse root over of n1 square minus n2 square divided by n0. So it will be equal to, you just have to put the value sine inverse root over of 1.50 square minus 1.40 square, 1.40 square divided by 1.33, because n0 is the refractive index of the outer medium. So if we put the values in the calculator, then finally the answer will be 123.9 degree. So this is the value of the acceptance angle. Okay, so this is the value of the acceptance angle. So first we have to calculate the numerical aperture. From numerical aperture, if you know, then you have to find out the acceptance angle. This is the general formula. When the outer medium is air, obviously n0 will be 1. In that case, only sine inverse root over of n1 square minus n2 square. So by doing all the numerical, you can understand that there is nothing to think, but you have to just apply the put the values on the formula. If you do it, then you can get the answer. So this is about the total optical fiber, where you have to know about core, cladding, their differences, their function. And one more question, that is your assignment. You must note down. The assignment is, what are the advantages of numerical aperture, or what are the purpose, why we use optical fiber, that you have to know. And also another question is, what is the physical significance of the numerical aperture. So this question you must prepare on your copy. So you can use Google, you can use your exercise book, whatever, but you must prepare your answer. Okay, and also you must note down all these formula somewhere, so that you can get it anytime. So thank you for today.